This whole chapter is about polynomial power and rational functions. So we will get to the rational part more in depth if you didn't understand the complex fractions and whatnot that we did before. We will hit on that some more. But today we're going to focus on linear and quadratic functions. You have done all those, so this should not be hard. Before we get to that, let's define some stuff. Yeah. Is it the same thing?
Non-negative.
0. Which set would 0 go in?
Non-negative.
Is it included in the positive?
No.
No. I know this seems dumb, but I'm telling you, as we start defining some stuff, you'll need to understand the difference. How would you describe the set of integers? Just integers. If I asked you in set notation, remember how we did this? Dot, 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 comma. We got some stuff in here. Dot, dot, dot. What numbers, if I wanted it to represent integers only, Carter, what would you put in the blanks? And I would probably also include the 0 in there, so we make sure that we're not talking about the set of positive numbers. I'm going to include a negative and a few positive. This is how we would describe the integers. Notice how we included the 0 and the negative. That's necessary here, so we pick up on that pattern. Okay. What's a polynomial? Carter. What's a polynomial? Define polynomial. Carter, define polynomial for me. It's a number? No. Give me some, okay, if you can't define it just yet, give me some examples of polynomials.
Wait.
I know. That's okay. What do you have? Of what?
Square.
Well, let's go back to the Algebra 2 definition, and then I'll give you the pre-cal definition. Okay, 2x plus 1, that is a polynomial.
I haven't even looked it up yet.
Give me another one.
X squared plus bx.
Okay, x squared. That is a polynomial. That is a polynomial. Give me another one. Anybody?
X3.
Plus what, Carter?
Plus
That-
x. Plus 6 and 9.
That is indeed a polynomial. Okay, so what is a polynomial? Because this is a linear. We know that this is quadratic. What's this one called? A cubic, but yet they're all polynomials. So what is a polynomial?
Something with x.
Okay, so greater than or equal to 1. I'm not going to call it a number. What are these individual pieces called? Terms. Within these terms, there are some specifications. What are those specifications? We talked about them. Where, what's negative, or what can't be negative? It can. No. The exponent. My exponents must be non-negative. No, because they could be 0.
So what's the point of putting
Okay, you can put that if you want to in your notes. Okay. Exponents on x have to be positive whole numbers. Now, this is how we define it in Algebra 2. I hope you remember that this is how we defined it in Algebra 2. We went through all this, and then I gave you several, and I said, is this a polynomial or is this not a polynomial? Whole numbers. Now that we're in pre-cal, we're a little bit fancier. Yes. We say that a polynomial is defined this way. Okay, don't let this intimidate you. Let me explain what this is. This is just allowing us to say that this is the a that belongs with the exponent of 1. We start at 0. We work our way up until we get to some unknown number n. Okay, but I need to define what are these variables or these terms here. So my a sub n and a sub n minus 1 and so on and so forth until I get to, can I zoom out? Why don't you just ask that? Go ahead. You're actually going to write it down. I'll wait. We're waiting on Carter to write it down. He finally decided to write it down. I don't know.
I'm feeling
All of these a variables are really just the coefficients. So for each one of these, I'm going to say that these coefficients have to be real numbers. This means real numbers. Meaning I can't have an imaginary number. It wouldn't be a polynomial any longer, okay? And not only does a sub n and all of the a's, not only do those have to be real numbers, but my value of n, well, that's already a given. My value of n is a, what? You sure? My leading coefficient here would be what? A what? There's a bunch of a's in here. A sub n, can we say that as a sub n? What would my degree be? N. Okay. It's just a fancy way of writing the definition of a polynomial using some math terminology instead of the words that we wrote before. So let's look at a couple. You tell me polynomial or no. Y'all got that? Okay. Ready? This is definitely a function. I know it's a function because I've got it defined as a function here, f of x. So by defining it f of x, I know what does it mean to be a function? Well, what's it mean to be a function? Vertical line test, right? So I'm a function. Is it a polynomial, yes or no, and why?
Yeah.
Why? All right. What's a sub 0 in this one? Negative 1/2. But I don't see the x hooked to it like it said. Because it's 0. That's exactly right. It's still there. It doesn't matter. It's a 3, but it doesn't matter. Y'all see where we're going with this? I'm trying to go slow because y'all said I went too fast last time. Y'all okay? Basically, we're taking our working knowledge of a polynomial from Algebra 2 with our new notation of pre-calc polynomials, and we are just deciding yay or nay, is it a polynomial? That's my constant term. That's always going to be your constant term. A sub 0 is always going to be your constant because whenever I do x to the 0 is what? 1. Anything to the 0 power is 1. Why?
A0 equals 1.
Remember, those are non-negative numbers, non-negative integers, non-negative whole numbers. It's not a polynomial. Could I make it 3x squared plus 4x?
Yeah, you can because it's the square root.
Can I? I don't know. I'm asking y'all. Can you do that? No, you can't do that. Look, the square root of AB is the same thing as the square root of A times the square root of B, but the square root of A plus B is not the same thing as the square root of A plus the square root of B. You can't do that. You can't do that. So this is no. You can't split radicals. I couldn't say that this is the square root of 9x to the 4th plus the square root of 16x squared. I can't do that. Because if I did that, what I would have is 3x squared plus 4x, and that is a polynomial. No, because I can't do that. I can't do it. I can't do it, Robert.
Why?
Because it does. That's not a property of radicals. I can split multiplication, but I can never split. It's kind of like whenever you have this, you cannot do this. No, not with addition or subtraction. No, not it depends on if it simplifies down to a whole exponent, a whole number exponent. All right, let's talk about some types of polynomials. I think we've already talked about most of them. Y'all know these, right? Linear, quadratic, cubic. What about a power of 4? It's a quintic. Power of 4, so if I had x to the 4th plus 6x squared minus 3. It's quartic. 5th is quintic. Sorry. We don't go past 5, having to know. All right. Remember, this is the intro section. It's going to sound basic, but we're kind of introducing some new vocabulary and some new stuff. Are you okay, Carter, over there? So today we are going to be focused on, okay, tell me when you got it. Today we're going to focus on linear and quadratics for the polynomials we're going to look at. God knows. Define linear functions for me. If you had to give me a definition. Not a graphical definition. Not graphical. Okay, ax plus b. But give me some more definition there. That's actually, we call it mx plus b, but either one. But tell me in terms of a polynomial. Ax plus by equals c. But it doesn't matter. It doesn't matter. Give me in terms of a polynomial. Some of the things that we've talked about with polynomials and everything else, tell me how we can use that to describe linear functions. What exponent? Okay, keep going. It has to have a degree of 1. Agree or disagree?
I agree.
What does that mean? Tell me what it means. Somebody say what it means. Exponent, the biggest exponent. Yes. Okay, so based on your definition, a linear polynomial or no? Can I manipulate it? So in this, I'm going to add must be able to look like this. Okay, so yes. No. So you're telling me this is not a line? It's a line. It's not a well, it is a polynomial because by the definition of polynomial, it is a polynomial. What does this look like? At 7, it's a horizontal line. Y doesn't change, but why is it not a linear function? You told me it's not. The degree is not 1. It doesn't have an x. What's the degree here? This has a degree of 0. What type of function is that? We learned it in Algebra 2. Yes. Constant. It's not, in fact, a linear function. It is a constant function. Linear function or no? Tell me why. Okay, there's no y. It's not, this one's not a constant. This one, if you graph it, looks like this. Why is it not a linear function besides there's no y? Okay, well, there's always a degree. The degree is actually 1 here, right? That's the biggest. But what's the problem? It's not a function. Why is it not a function? It does not pass the vertical line test. This 1x value has infinitely many output values. It can't be a linear function if it's not even a function. See where we're going with this? Yeah. I'm going to teach you 2 new words. Let's at least finish linear functions. We'll take a break before we do quadratic. All linear functions are what we call oblique. Underline this, highlight it. This will come up many, many, many times in the very near future. Oblique means it's neither horizontal nor vertical. Sometimes you will hear it called a slant line. We will start finding asymptotes that are slant asymptotes or oblique asymptotes, and you need to know what that means. Okay. No. Neither horizontal, not horizontal or vertical. Bless you. All right. Let's talk about how we write the equation of a line. This is easy. This is linear, y'all. We're easing in here. Let's say that I told you I have a function f, and f of -1 is 2, and f of 3 is -2. And I want to write the equation of the line that goes through those 2 points. F is a linear function. What do I need to write the equation of a linear function? An m, and m is what? Slope. What else do I need to write the equation of the line? Not necessarily. It could be, but we need a slope. What? You are lying.
Wait, why is it called it?
To write the equation of a line, I need the slope and a point. Only instead of calling it a slope now, I'm going to call it the average rate of change. So I agree, we'll call it AROC. AROC. In calculus, we do AROC and IROC, and here we'll just stick with AROC. All right, so let's talk about how we find this average rate of change, which is nothing more than the slope. It's a fancy way of saying slope, okay? But if I say AROC from now on, you'll know, oh, she's just talking about slope. Carter, when I say A-Rock, what am I talking about? Thank you. How do you find slope? Okay, that's basic definition. How do we find it? Okay, y1 minus y2 over x1 minus x2. Let's sophisticate it just a little bit. Let's say I have f of x, right? This is my function. If I want to find the average rate of change between x equals a and x equals b, okay? My 2 points on this line are a, and then I plug it in, right, to find y. So a, if I write it like this, do you understand? A, f of a. It does make it worse. It's the thing with pre-calculus and calculus. It's going to make it worse before it makes it better. Because in order to do the things that we're going to do a little bit later, you're going to have to be able to do this. Geniuses. Okay. How would you write the second point b following this same notation? B, f of b. All this is saying is to find this y value, plug b into the f equation. Okay? Now I'm going to make it even worse. Give me, based on just this, give me an equation for the average rate of change. Okay, say it again. Say it again. F or f of b minus f of a over b minus a. Either of those is acceptable. That is the formal definition for A-Rock. But I could have just given you that and you'd go, Miss, okay, this is too much. But understanding that it's nothing more than slope between 2 points whose x values are a and b, do you understand where this is now coming from? What an idiot. Carter, we are not in kindergarten. What the heck? I heard, I know. Okay. Okay. Now, look. This needs to be starred in your notes also. This is a big player. Formal definition of A-Rock. Now let's go back to the example we were trying to write. Yep. Oh, thank you. I'm glad I have your permission, Carter. Using that formal definition. In this example, my A would be -1, my B would be 3. Do you agree? What is A-Rock here? For this particular example. I know that f of -1 is 2 and f of 3 is -2. What's the average rate of change there? I gave it to you in the beginning. So,
Oh my gosh. Brain break.
go. You'll get just as much if you go to the bathroom as you're getting sitting right here, but the rest of us will get more.
I beg to differ.
Nope, nope. As long as if you start with this one up top, then you start with that one in the bottom. So if you did f of -1 minus f of 3, on the bottom you'd have to do 2 minus -2. So you have to flip both of them. All right. Yep. I want y'all to see that we're doing a really simple concept, but we're doing it a difficult way because everything's going to get a little bit harder soon. Oh. Because this is the point -1, 2. This is the point 3, -2. Oh, yes. No wonder y'all are confused. Sorry. Sorry, I messed up. Look, it's y's. It's y's over x's. Rise over run. I haven't plugged them in yet. What? F? Oh my gosh, y'all.
Where'd you get 2?
It was an example. In the beginning, I said.
Oh, there. Go back up. There it is.
No, that's why I circled it a minute ago. Y'all gotta stay with me. Y'all got to think through this. I know y'all can do this. This is not that hard. This is a brand new way. That's why. This is a brand new way. Oh. All right. Look. Remember the whole goal. We sidetracked over here on A rock and what is A rock. But at the end of the day, what we were trying to do is, given these two values, write an equation of the line for f. And f is linear. So the first thing I did was find the slope. And slope is the same thing as A rock. So I went through and found A rock. Right? This point is -1, 2. This point is 3, -2. So to find the slope, it's just rise over run. It's just written funny. Okay? So I've got -4 over 4, which is 2 minus 2 is -4. 3 minus -1 is 4. No. 3 minus -1. All right, listen. I know y'all don't like this. I'm sorry. You're gonna have to be able to recognize this form and this form. That is the way it is going to be given to you from now on. We are gonna make definitions from this. So you have to understand it. We're doing an easy example with this, but they're not all gonna be this easy. I'm using an easy example to show you how it works, okay? Stay with me. I know it seems senseless to use this for such an easy example that you can just look at it and do slope for, but there's a reason, I promise. It goes all the way up to calculus. Bert, you are killing me. What? Because it's the y values, -2 minus 2. Yes. Let me write the equation, then we'll do another one. So remember, the whole point in this is writing the equation of a line. I have the slope. What do I need to write the equation of a line? I need a slope. Got it. That's A rock. I also need a point. Lucky for me, I have 2 of them. 1, 2. Pick one. It doesn't matter which one. -1, 2. Negative 1, 2 is my point. My slope is negative 1. How do you write the equation of a line given a point and a slope?
I was repeating that like.
Point slope form? I didn't hear you, I'm sorry. If you do not remember point slope form of a line, it is the best equation, in my opinion, of a line. We can manipulate it to get to any other form, but we want to start with point slope form because that's what we have as a point and a slope. So here's my x1, y1. Here's my slope. Y minus 2 equals slope x plus 1. Now it asked me to write a linear function as a polynomial. Okay, so I've got to make sure it's in standard form of a polynomial. So let's go through. We're going to solve it for y. I'm just going to distribute this negative 1 through. What do I do now? Add 2. So y equals negative x plus 1. And because my original problem gave me points in the form of f of 1 and f of 2, I am going to change this to say that f of x equals negative x plus 1. That was way harder for us to get through than what I had anticipated. That's not all. So these are the y values up top. These are the x values. The x's are what's in parentheses, and the y's are what follows. Oh, you're saying that's what you got. That's what you were. Okay. Here's essentially, well, you may also, let me just show you this. You may see this form. We talked about rise over run, y2 minus y1. I think I've shown y'all this before. If I haven't, I apologize. This is a notation also that we use a lot of times for slope or for change. Delta is just the Greek letter that means change. So delta y over delta x literally reads change in y divided by change in x. How does it change from one point to the other? And it's the same thing. I'm going to let you take a little break. We're going to come back and talk about linear correlation and modeling. And that's strictly on your calculator. And then we will probably stop there for today. Yes. You need to run to the bathroom, go to the bathroom. And if you do not, if you do not remember how to do it, boys and girls, we will be entering data on our calculator and letting the calculator find the linear regression model. Now, as we do this, there are going to be some additional things that we look at. If you look at the sheet that Cricket brought you, if you did not know how to do the linear regression before, look at the TI 8384, and those are the steps to input. If you have an Inspire, I don't know that anyone in here does. I've got several in my second block class to do. This goes through and tells you how to find the regression equation. Okay. Let's talk about regression and what it means and correlation. Carter. when we plot points on a scatter plot, sometimes they will have what we call correlation. That means how tightly they are, they resemble a linear model, okay? How tightly they're grouped. So if we have something that looks like this, that follows, that really looks like a line, right? You agree? This is what we would call strong positive correlation. The positive is referring to the slope, okay, because it's going up. So that looks like it has pretty strong positive correlation. I could still be positive, but maybe not as strong. So maybe it looks something like this. It still is going up. It looks like it could follow a line. A line of best fit might look something like this, or I guess more like that. But it's still, you can still tell it's positive and going up, right? But it's got weak. Positive correlation, okay? From there, oh my gosh, we can have strong negative correlation. I put correlative. Or negative. Weak negative. And you can also have no correlation at all, little or no correlation. So if it just looks kind of random, it doesn't look like it's following any line. It doesn't really look like it's, I would say that that has little or no correlation. Weak. Negative slope. Now, this should be a review from Algebra 1. You should have done correlation in Algebra 1. I hope you did anyway. If you didn't, it's a pretty easy concept, okay? When you calculate the linear regression, you may have noticed that sometimes you get, and I think there's a different one you have to put, but we have what we call linear correlation coefficient. And this is getting into a little bit of statistics, but we use it a lot in Algebra 2. We use the variable r, and it describes the correlation for us, okay? And what happens is r is always going to lie between -1 and 1, inclusive. Here's what it tells us. No, it's okay. Good. If r is positive, this means that there is a positive linear correlation. If r is negative, that means it's a negative linear correlation. If the absolute value of r is 1, meaning R is either 1 or -1. That is the strongest linear correlation you can have. What do I mean by that? They look like this. Like the points literally lie, all of them lie on a line. It is almost impossible in a real life situation to get something like a 1 for correlation. No. 0 also is near impossible. But 0 would be no correlation. I think I'm going to stop there. Let me give you your work.